what about quarks? Okay, so this factor, 7/8, this is a famous factor to represent the difference between the bosonic particles and fermionic particles. Okay, this comes from the distribution function, the integration of the distribution function. Okay. Anyway, so here are the two spins, spin up, down, and the particle, antiparticle. I'm now talking about the zero density world. So you have as many as you have the antiparticles as many as the particles. Okay, and the flavors 2 to 3. I mean, the strange quark mass is something around 100 MeV. Okay, and now I'm talking about the temperature 200 MeV. So you have definitely two flavors, U and D, but definitely not three flavors, okay? But so something in between, okay? So the strange quark mass is always a source of the headache, okay? So because the strange quark mass is comparable to a lambda QC, it is not heavy, it is not light, so it is always something intermediate. So you know it makes the physics very complicated, okay, in many circumstances. Anyway, the three colors. So that means you have 20 to 30 quarks. Okay. So in total you have 40. Okay. So that is a big difference from this. Okay. Ionic world. And then if you look at the thermodynamic quantities like pressure or entropy density or energy density, internal energy density. So you know the Stefan Boltzmann law. Okay? If you can neglect the particle mass, then the pressure should be something proportional to T to the fourth, because T is only available dimensional unit. Okay? If you neglect the particle mass. Okay? And then this coefficient, the overall coefficient must be proportional to the number of degrees of freedom in the system. Okay? And so, in the pion case, I mean, in the hadronic phase, this degrees of freedom should be 3, as I explained. And this must jump to 40, okay, around 40. So there must be a big jump if you look at the pressure, okay. And if you have two systems, or if you have two possibilities in the system having different pressures, then if the pressure is greater, then that is energetically more favored. Okay, that is quite natural, right? Because okay, if you have one system and in some region that system has one state of matter having some pressure, and in some different region that pressure is something different. And if the pressure is greater, that dominates the system, right? The kicking out the less pressure for the states, right? And so the biggest pressure means the most favored state. Okay, the ground state can be identified in such a way, or in other words, the smallest free energy. Okay, the energy should be small if the state is most stable. Okay, and this pressure and free energy, they are related by minus sign, right? The Helmholtz free energy is just minus P, okay, except for the volume part. And so you may have a question here. Okay, as I said, the quark-gluon gas has a bigger pressure as compared to the pion gas. Then why we can have pion gas in the low temperature phase? Okay, if the temperature is low enough, we know that this pion gas must be the ground state. Okay, as compared to quark-gluon gas, even though the pressure looks like the quark-gluon gas seems to have a larger pressure. And the answer is that in the vacuum, you have non-trivial, non-perturbative contribution from the vacuum properties. Okay, that is the back pressure. Okay, so at high temperature, certainly the pressure is given by this expression. Okay, but in the confining vacuum, the vacuum itself is very non-trivial, having lots of condensates in it. Okay, and that condensate gives some contribution to the energy density or pressure. and that is called a back pressure. And this quantity is related to the Gouron compensator. I mean, the FF is a gating variant quantity, and if you measure the expectation value, vacuum expectation value of FF, it could be something non-zero, right? And indeed, it is non-zero. That can be measured on the lattice, for example, or that this value can be determined by some phenomenological fit to the observed hadron spectroscopy or something. But anyway, so it is known that this value is something around 200 MeV. So again, this is quite consistent, right? Because, you know, as I said, everything should be characterized by lambda QCD. And this is precisely something comparable to lambda QCD, right? And then, so this hadronic pressure is pushed up by this back constant contribution, okay? And so, as long as the temperature is small enough, the hadronic pressure is always bigger than the pressure of the Gouron gas. And that's why this hadronic phase is more favored, okay? But at some point, because this coefficient of the tip to the fourth term is greater here in the case of the Gouron plasma, of course, at some point of the temperature, this part of tip or Gouron gas, this pressure must exceed the hadron gas, okay, pressure. And then there must be a phase transition here. And from this simple estimate, you can make a guess about the critical temperature. And that is, of course, this scale is provided by this back constant. And this must be, I think, should be, well, the dimension is something strange. This must be maybe to the power over 1/4. Okay? Anyway, so this is a 200 something. And so this coefficient, this is well, this number is something strange. Anyway, this TC must be given by this back pressure, and this because this back pressure is of order of lambda QCD, this phase transition temperature is naturally of order of lambda QCD, so 160 MeV in this case. But anyway, something around lambda QCD. Okay, everything is quite consistent. But so this picture always leads to the first order phase transition. Okay, but that is so because I use a very simple model. But in reality, the situation is a bit different. Okay? So this is one example of the lattice QCD measurement of the pressure. And indeed, around the temperature, lambda QCD, namely 200 MeV, you can see a big change in the pressure. Okay? Pressure divided by T to the fourth. Okay? So this essentially counts the relevant degrees of freedom inside of the hot system. Okay? And so here, only pions can be excited. So this should be something 3 times some the sum factor, like a pi square divided by 90 or something. Okay, and this jumps into some bigger value, approaching a Stefan Boltzmann limit. Okay, so this is still below Stefan Boltzmann limit by the some residual interaction effect. But anyway, so here you see some phase transition. Okay? But this is not really the first order phase transition. But actually, this is rather the smooth crossover. Okay? There is no true phase transition, but smooth crossover here. Okay? But it is very important to note that the pressure is always continuous, regardless of the order of the phase transition. Okay, I sometimes hear that some people say that, oh, here, so look at this behavior, everything is smooth, so that there is no clear phase transition, but this is only crossover. Okay, this is a wrong statement, because the pressure is always continuous, even when it is first order phase transition. Okay, so you have to look at order parameter behavior or entropy. Okay, or I mean the derivative of this quantity. The pressure is always continuous. But anyway, it is known that So in this case, what happens is crossover, okay? Not the phase transition, not the part of the phase transition. So in reality, the smooth crossover is the answer. And so the question is how to understand that. And definitely, this bug model description is insufficient. Okay? So how to understand that? And for that purpose, of course, we have to look at order parameter for their confinement. Then, what is the order parameter for their confinement? Okay? So to think about that problem, let's put some test cork inside of the system. Okay? So this is an infinitely heavy cork, or this doesn't move. Okay? This is test cork. So just put some probe. Okay? And then, so here you put cork, and here you put anti-cork, and naturally they feel some interaction by their some glue interaction. Okay? And if this so this system in the confined phase, the energy gain by the presence of a single cork must be infinitely large. Okay? Otherwise, you can put corks inside of the system. Okay? And then that situation is far from confinement, right? So confinement means you need infinitely large energy to put one test cork. Okay? That is the situation in the confined phase. Okay? So in this way, maybe you can characterize a confinement or confined or deconfined phase. Right? So let's introduce this quantity, the free energy difference. Okay? Free energy difference between the situation with and without a single cork, test cork. Okay? And then in the confined phase, this is expected to be infinitely large, and in the deconfined phase, this must be something finite. Okay? And then let's think about this quantity. Okay? Just exponentiate this free energy on the exponent, the exponential. Okay? And if f is infinitely large, then this is exponential minus infinity. That is 0. Okay? So in the confined phase, this is 0. But in the deconfined phase, as I said, this f is something finite. That means exponential minus finite quantity is of course finite, right? Non-zero. So in the deconfined phase, this quantity is something non-zero. And so this is precisely the behavior you want to have for the order parameter, right? In the confined phase, it is 0, and in the deconfined phase, it is something finite. So this is precisely the behavior of the order parameter. And this quantity defined in such a way is called the Polyakov loop. Okay? Why loop? This I will come back to this point later. Okay? Anyway, so this is deconfinement order parameter. And so let's try to look at the Polyakov loop correlation function. Okay? And actually, this Polyakov loop correlation function is related to the heavy cork potential. Okay? And that you can measure on the lattice. And so this is one example of such measurement. So below Tc to the above Tc, you can see that so at 0 temperature, you have some linearizing potential behavior that is expected as the confining force in the vacuum. Okay? But above Tc, the potential is flattened. Okay? So there is no confining force if the temperature is high enough. Okay? So this is precisely the expected behavior for the heavy cork potential. And the point is that if you consider the Polyakov loop correlation, that corresponds to the free energy gain by the presence of a cork and anti-cork. Okay? So in the previous slide, I talked about the free energy associated with the presence of single cork. Okay? Not correlation function, okay? But single cork here, this point. Okay? But here, I'm talking about the correlation function. That means the free energy difference associated with the presence of quark and anti-quark. Okay? And if this separation distance is large enough, you can naturally expect some decomposition. Okay? This quantity must be simply given by the multiplication of this quantity times this quantity. Okay? This is a very natural expectation, right? If the distance is large enough, okay? So they do not talk to each other anymore. And then, if the correlation function has a linearizing potential in the confined phase, of course, this quantity goes to 0 if R is large. Okay? Because this is exponential minus string tension times infinitely large distance. So this is naturally 0. And that means this quantity and this quantity, they must be a 0 also, right? And so in the confined phase, in this way, you can also understand why this quantity, namely the Polyakov loop, must be 0, okay, from the behavior of the correlation function. Okay? So everything is quite consistent, right? So this scenario makes sense, and also from the heavy quark potential, you can understand the same behavior. Okay? In the confined phase, you must have 0 Polyakov loop. Okay? But the nature is not so kind in reality because of the string breaking. Okay? This scenario makes sense if you do not have dynamical quarks. But in reality, the system has dynamical quarks, and that means this string can be broken by the excitation of a pair of quark and anti-quark. Okay? So if this free energy gain, FQQ bar, becomes greater than the energy that is necessary for the pair excitation, okay? This excitation. Then, of course, this state is energetically more favored than this string configuration, right? And so, this FQ cannot exceed to this hadronic scale like 800 MeV. Okay? 800 means the vector meson mass. Okay? The vector meson is the low meson mass, for example, is 770 MeV. And so more or less, this Polyakov loop value, or this single quark excitation energy, cannot exceed the typical vector meson scale. Okay? So this means if you take account of the quark and anti-quark excitation, okay, this doesn't hold anymore. Okay? But this value, F, is at most 800 MeV or something. And so this Polyakov loop can never be 0. Okay? So there's actually no clear distinction between confined phase and deconfined phase. Okay? No clear qualitative change below and above T6. And that you can also see from this behavior, the behavior of the heavy quark potential. Okay? So this is a simulation in the presence of dynamical quarks. And indeed, okay, even below Tc here, okay, these black dots, the potential is saturated. Okay? So it doesn't grow linearly forever, but it is actually a flattened at large distances.
So actually, if you change the representation for the quarks,
yes,
instead of being fundamental and fundamental, do you expect different behavior?
Oh, the fundamental. So I'm talking about the fundamental
yes,
quarks.
So,
okay.
But now, if you change that, do you expect something sharper? Like
the adjoint representation behaves like blue ones. Okay, so it doesn't break this string.
Right.
And so yes. So the situation is very similar to the situation without fundamental quarks, without quarks. Okay. So the pure Gronic situation. So you still have the clear phase transition.
Or
yes.
Maybe if you say if you do this kind of computation, you find the quarks, and then if you change the boundary, you try to preserve some
that is possible. Yes, that is possible. But that, of course, to get the physical information, you have to take the thermodynamic limit. And in the thermodynamic limit, that projection is actually removed. And that idea is closely related to the so-called canonical description. Okay? And if you fix the number of quarks, the center symmetry is superficially restored. But that projection is removed in the limit of thermodynamic infinite volume situation, and that you can prove. Okay? So it's a bit dangerous argument. But yeah, actually in 90s, there are lots of papers about that, trying to see some unknown order parameter for deconfinement even in the presence of dynamical quarks. Okay? So nowadays, people do not believe in such idea anymore, but actually, some decades ago, people, thought about that possibility. Yes.
In the case with the fundamental quarks,
Yes.
if I think about the gluon analogy, can I sort of pull two gluons, then we produce a whole bunch of gluons? So essentially, you also break strings.
Gluons are close to gluons.
Right. Right. Right.
Okay, I don't see
Okay,
when you pull a
Yes.
glue, when you try to separate two gluons inside glue ball, can you sort of
So
make it
I mean, okay, this is not a single, gluon configuration, but this is a bunch of gluon, okay, producing some energy flux tube. Okay? And this is the QCD string, okay, so-called QCD string, and as David said, the closed string, the QCD string corresponds to the glue ball. And so it doesn't break this flux tube. Okay? So anyway, in any case, okay, in some sense, it may be possible to define at least approximate order parameter for deconfinement. Okay, but order parameter means you must have some symmetry. Okay, otherwise the order parameter doesn't make sense. So then the question is, what is symmetry? Underlying symmetry corresponding to the order parameter. And the answer is center symmetry. And center symmetry is a bit non-trivial symmetry that exists only for finite temperature non-abelian gauge theory. Okay. This is a